with an insightful first lecture. Continuing this momentum, we now commence the second lecture, where she will speak on different types of machine learning algorithms and their applications and technologies which fuel the growth of AI.
Okay, well, thank you again. Hi, thank you again. And we now continue with lecture 2, the course in AI and machine learning algorithms. So lecture 2, different types of machine learning algorithms and their applications and technologies which fuel the growth of AI. I know I stand between you and the break, so I'm aware of that. But let's begin, okay? So, lecture 2, again, different types and applications of ML leading to AI. So, here's an outline. We begin with the science of machine learning algorithms. Okay, so the science behind it. What is the scientific and mathematical basis for machine learning? Then we go into the types. Then we look at an overview of AI. How did AI emerge? Okay. AI and machine learning, how do they merge the two? And then, of course, AI applications in everyday life. So today we are just going to look at the overall applications. We are going to look at specific studies later. Wrap up and takeaways, and of course, I will leave you with a motivational quote. Okay, so we always begin our session with a 1-minute meditation. We end to learn from data, which is really data science. There's also majors in data science, as you are already aware. Okay, so those are the ones that allow actually focus on how does a computer learn from data, and rather than, of course, follow the pre-programmed rules, which is the traditional coding that we talked about earlier. What are the scientific or mathematical underpinnings of machine learning algorithms? So what are the foundational base for machine learning? And there are basically two, okay? Function approximation and probabilistic reasoning. So we will dive in depth in each one of these, okay? That's what we will do. So what is function approximation? The assumption, that underlying assumption that there is a function that relates the input to the output. So that's where we begin. We assume that there has to be a relationship between the input and the output. Okay, so that's our basic assumption. There has to be an underlying function. Now our job is to find what that underlying function is, but that's where the assumption begins. It's the output has to be connected, is connected to the input. Okay, that's a given. That's our basic underlying assumption. So a technique for estimating an unknown underlying function using available observations. But we don't know what that function is, correct? Okay, we assume there has to be a relationship between input and output, but we don't know what that is. And so our job is to find out, hey, what is that relationship? What is that underlying function? Which have the algorithms. That's how we design the algorithm. So we design it based on that assumption. So we look at all different avenues. There is nothing that restricts us to doing one thing versus the other. Okay, so we have to look at all possibilities because we don't know what that function is. It's unknown to us. So here we are talking about, I'm just giving one example. We are talking about approximation of an inverse square root, often called AISR. That is quite common. That is the function that you see, the bold line where you see the function, and then you have iterations of that function. Okay, iterations is modifying that function into different, adding terms to it, taking a polynomial, adding terms to it. That's where the mathematical basis comes. So if there are people here with our math majors, some of you were faculty that I met on Saturday who are math majors, you would contribute heavily to this development of the algorithm. Okay, so that's where the design, applying an algorithm is one thing, designing an algorithm is another. Okay. So function approximation, how does it work? Approximate an unknown function fx using available data. We all know typically anytime we call it a function, we all call it a function of a variable, right? Okay, and there can be multiple variables. Of course, we know that also. It's not just x, y, z, whatever, okay? So using the available data, we conceive what that function is going to be, the unknown function. What does available data mean? So available data is only what's available to us. One thing we have to remember is that we may have a very narrow data set. Okay, so the function that we design for that application may not fulfill, may not be able to be extrapolated to something else, only because our data set was so narrow and not robust enough to develop an application which has wider, to develop an algorithm which has wider application. Okay, so one thing to remember is that the available data does mean something. Okay, we have to look at what is the available data. There are always limitations on what the data set you are going to deal with. Okay, and you have to be, as a designer of an algorithm, you have to be aware of those limitations. So the first thing to do is actually look at the data set. That is the very, very most important thing, is to know in and out what that data is, what are the inputs, what are the outputs, what are the limitations on that data, so on and so forth. Okay, so do not ignore the value of learning what the data set is. Second set of input-output data pairs, we are looking at that because we assume that there is an underlying function that relates the inputs to the outputs, right? So if our assumption is that, then we have to look at what are the inputs, what are the outputs. So that's why we talk about input-output pairs. Why? Because that's where we begin with that assumption. The goal is to apply a known function, because that's how we can actually address it, right? Beginning with known, going to unknown, okay? The goal is to apply a known function gx that is as close as possible to the unknown function fx. So the unknown function we really don't know anything about. So we begin with known functions and we try to apply them to that data set, okay? And see which one fits, okay? That fit is a very technical word, okay? So assume a polynomial fx, and you see all these terms. It's a 6 degree. What is the degree or order of this polynomial? 6. Okay, very good. So here you see all the degrees of the polynomials, how it is. When it is a 0 degree polynomial, what does that line look like? Right, okay. I'm just refreshing the math for you in case you have forgotten. Okay, it's going to look like a flat line because, just the y-intercept, that's it, because y equals x, correct? Okay, and then the first degree polynomial is going to be a straight line with a slope, correct? Then you see the second degree polynomial, the third degree polynomial. The yellow dots, by the way, that's what the data is. Okay, so you see the data, which are those yellow dots. So now we are going to try to fit the polynomial to the data set. And as you see, the 4th degree, 5th degree, 6th degree. Okay, so now let us understand it's 6th degree or 6th order polynomial. You can call it either 6th degree or 6th order. Original data, what do you think, was generated by what degree polynomial? Anybody? You can show like hand, 1, 2. You can show that. You can show it with hand rather than shout a number, because I cannot hear you very well if you speak softly. No, in this picture. I'm not talking about some data set out. I'm talking about just this picture. Original data, what do you think was generated by which order polynomial? Okay, what do you see about the fifth and sixth degree polynomial? Anybody, can you comment on what do you see about the fifth or sixth degree polynomial? Do you see that they are almost the same? Do you see that? Okay, so then what do you think it would be the fifth degree? Because the lower the better. Remember, do not complicate matters. Okay, that's another thing. Okay, don't try to over design a system. Design it efficiently. That's where it comes, it becomes efficient. So don't over design. Don't say, oh, we never over design for something. Okay, unless it is like humans are involved and everything, then we need 100% redundancy and everything like that. But otherwise, for general systems, we don't over design. We just design it right. Okay, because we want to keep the cost down. Remember that. Economics also plays into any development. Anytime you're developing technology and economics goes together. Okay, just designing something for the sake of designing, making it fancy, but if it's so expensive, nobody is going to implement it, nobody is going to use it, right? Okay, so always design just right. That has to. So this would be a fifth degree polynomial, might fit just fine, that data set. Okay, so stay with the fifth degree, no need to go to the sixth degree. That's why I brought this problem to you. Okay, so to show you the efficiency of an algorithm. So was it missing any terms? If yes, which order terms do you think might it be missing? Just in general. What do you observe?
I think outside present 360 degree 5.
Okay.
There are few points that far away from
Right, but we are trying to design as close a system as possible. Do you see the fourth degree polynomial? Does the fourth degree polynomial actually fit the data? Do you understand what I'm trying to say? Do not use polynomial terms that you don't think are fitting the data. So then drop those. Okay, so the idea is for us to develop a efficient function. The whole idea is about efficiency. Okay, not just to design it, and then you run iterations for it, because some of our experiments would run for, like the computer networking and stuff, they would run for 24 hours, 16 hours, because of the iterations that are needed to actually make it as near to perfect as possible. There is nothing perfect in this world. There is nothing 100%, right? We always come as close to 100% as we can. So, and here I thought I'll blow up the picture just for your own, just to, make the point that remember to design. And the whole idea that I'm trying to convey here is the function designing has to be efficient, okay? And that function approximation is a big deal, because you have to know the data set in and out. Every data set is going to have limitations, and there's only so much that you can extrapolate or think beyond. Okay. Now, why use function approximation? The goal is to find a known mathematical function that closely resembles the behavior of a complex unknown. The known mathematical functions belong to a well-defined class. For example, polynomials, neural network. Neural network also uses different, we are going to talk about Bayesian networks. All these are mathematical concepts. If you are a computer science student, okay, and you don't think you have a strong basis in math, I would highly recommend going and doing some math courses for your computer science, because not all computer science programs are designed to. I started my career in physics. So with physics, if you don't have math, then you can't do physics, because physics is really applying, right, for all different. So my math background was really strong before I went into computer science and learned coding. When I first learned coding, it was all Fortran. Then I myself transition to Pascal, C, C++, Java, all this. If you have the foundation in programming, you can learn the new programs. Okay, these are just languages that have different ways of application. So remember one thing: what you're learning today is going to be outdated in 5 years from now. Just assume that. Okay, what you're learning today, the fundamentals are something you need to absorb, the foundation, and then build upon that. The applications are going to change all the time, because what applying today, those will be age old in 5 years. Okay, the foundation is going to stay. So remember, the math is not going away. The math stats that we learn, that is not going away. Now the math even is becoming more like the using the functions. How to use the functions creatively is part of it. So data fitting, remember a little while ago I said fit is a technical word. Don't think of it as something small. Data fitting is where available data points are used to estimate the function. Why? Always remember, it's available data. It's not all the data that's possible that you can get. You have a limited data set. Okay, so be aware of those limitations of the data. When the order of the approximating polynomial matches the order of the polynomial in the original data, the closer the fit. Make sense? Okay, the order of the approximating polynomial, like we learned in the previous picture, matches the order of the polynomial in the original data, the closer the fit. So that's why we saw how the fifth degree polynomial was closer to the data. Yeah. Correct. Right. And that's why I talked about the fifth degree versus the sixth degree. I said sixth degree is not needed for this. Remember? I said stop at the fifth degree. So otherwise we would be overfitting. You are absolutely, we are going to talk about overfitting. Absolutely. Right. Right, and that's where your all data, there is never a perfect fit. We have to remember that. Okay, never ever are you going to get a perfect fit. You have to come as close as possible to the data. So there are always going to be things or cases, okay, that are going to be outside, which will not be addressed by your algorithm. And that's where the limitations come into play. Even your data set is not complete, right? It's not complete. It's always whatever available data is. So even if we try to fit it exactly to that data, that algorithm may not work in a different situation.
Does it mean that we should at least go for to take polynomial and finding out the base on what will happen in the field? No, nothing is perfect in mathematical approximation problems, right? So in this case also, sixth one is good, but it will increase complexity to the model also. So fifth one is nearer to the approximation, nearer to the optimal solution. We should go with the fifth one. In general case, does it mean that we should at least go with the polynomial functions and find it out the best one among them?
Correct. 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 Absolutely. We cannot stick with one function. We have to go with multiple different options and try to see which one fits. Right? That's why we start with known functions, gx and gx, hx, whatever are those, and then see how that fx is going to align with each one. Absolutely. Because data is unknown, the function is unknown. Correct.
Um, when the order, oh, okay, we already talked about this. When the order of the approximating polynomial matches the order of the polynomial in the original data, the closer the fit. The next step is prediction or interpolation. So, approximating a function to estimate its values at unknown points, right? That's where the prediction comes into play. How good is the function that is approximating this data? Okay, I have this data set. Now you take a new point, a known point, and say how well is the function predicting it, and is that what the output looks like for that. That's why in especially for the supervised learning algorithm, we have the test data on one side on which we test, but then we have the training data. So the training data is where we are trying to develop the function, right? And then the test data is where we are trying to test it. Technically, is this really different from traditional statistics? If you have done traditional statistics and regression models are exactly that. So regression is determining best fit, correct? Okay. So linear regression, I just picked a really simple one, nothing complicated. And as you can see all these lines, and we are trying to see which one would be the best fit for that data. Okay. So which line would be the best fit, which slope and so on and so forth. So regression is similar to function approximation, is what I'm trying to convey to you. So you might think, you are doing traditional math, traditional statistics. I'm doing ML. You are still doing, you are applying, taking those same concepts forward. Okay, is what I'm trying to say. So do not discount the value of your math foundations, okay, and statistics foundation. So, science of machine learning algorithms, we already talked about how machine learning, we have to look at data science, and we talked about function approximation. Now we will talk about the second underpinning, which is, does anybody remember? Probabilistic what? Oh, not this one. So what is probabilistic reasoning? Okay, let's talk about that. So we talked about function approximation. Now let's talk about probabilistic reasoning. Basically, it combines two concepts. Okay, probability with logic. Does it make sense? This is the probability of something happening, but then does it make sense? Okay. Probability indicates the uncertainty in knowledge, right? That's why we have probability. Oh, maybe it will rain. Oh, what is the percent, 80% chance that it will rain, correct? Logic establishes validity of inference. So now the logic, 80% chance that it will rain in what month? Okay, so, it's like, is it really possible? I like to always give humor. Okay, so let's look at this extrapolating problem. Okay, number of husbands 0 and 1. With 2 points, we can define a line. Everybody in mathematics agrees that. Okay, so with 2 points, yesterday you had 0 husband. He is telling the bride. Okay, tomorrow, today you have 1 husband. Let's draw a line. Hey, as you can see, by late next month, you will have over 4 dozen husbands. Better get a bulk crate on the wedding. Okay. You understand what the point is? The point is, we have to stop at the logic. This logic is crazy. Mathematically, absolutely right. Correct? You cannot argue mathematically but logically we know this is crazy. Okay, so that's where the probability reasoning comes into play. Okay, we have to look at the reason. We as humans can actually understand, hey, is this making sense? Whatever the computer is spitting out, this output, is that making sense? Okay, this is a good way. One way I like to convey points is through humor, and because then you tend to remember better. So why probabilistic reasoning? All complex systems are faced with ambiguity or uncertainty because there are no clear cut answers. For example, using, say, if then rules. Okay, if then is the traditional programming, correct? If this then that, very traditional programming. There are no if then rules necessarily everywhere, every time. all Almost all phenomena in real life are based on likelihood. It's not like if this happens then this will definitely happen. It is never like that. Okay, most likely it will happen, but there's always everything left to chance. So that's where the likelihood and probability comes into play. Decision making uses probabilistic reasoning based on quantified uncertainty. So now what does probability do? The whole probability theory is based on quantifying the uncertainty. And probability, don't think, if you have taken math, and probability is one of the pretty difficult topics in mathematics, right? Okay, just the concept of how to apply probability is not something simple. It is something that you need to delve in depth. So quantified uncertainty, evidence events represented as nodes, and I'll show you a picture of that right now, and prior knowledge, conditional probability, and cause effect relationships. Some key mathematical concepts in applying probabilistic reasoning are Bayesian networks. I think I referred to that a little while ago. Bayesian networks based on the Bayes rules or Bayes theorem, and Markov model. There are different variations of the Markov model, but these are I'm just picking two. There are more than that. Okay, I'm just picking two as an example. So let's look at Bayesian networks. The Bayesian theorem, what does it say? The probability of A given B, like this is standard Bayesian, right? Is you can read the terms, which is probability of A and B are those, and then the probability of B of obviously not equal to 0, and the probability of A given B means when the B happens is probability of B given A when A happens. Okay, and then the network. Bayesian network has two components, right? It has nodes or variables connected with directed arrows. Look at this picture, okay? Like this is a breast cancer in between. Look at how the arrows are going. They are the inputs, and then you have the outputs, okay? So now those inputs have to be linked to the outputs with a function, mathematical function. Are you getting some picture, some idea about the mathematical underpinning of an algorithm is? Okay, so the underlying assumption is we always have inputs and we will always have outputs, and there is a relationship between the two. So our job is to find what that relationship is, mathematical relationship. And that mathematical function, we then relate it to probability, because there is nothing perfect in this world. It's not like if then, I have these inputs, then these will be the outputs. It's not like that. That's where the next step comes into play, which is the probabilistic reasoning. There is a probability that this output will happen with these inputs, and then does it make sense in real life? Okay. So all these are the input factors, as you can see. Oh, they are blowing up. That's nice of them. Okay, to bring it closer. So these are the factors. I'll just read off the factors just for your information. Alcohol and smoking, hormones, menopause, because this is talking about breast cancer. Okay, this is about breast cancer. Pregnancy history, family breast cancer history. So these are the 5 different inputs for the breast cancer. What are the outputs? Skin thickening, nipple discharge, breast pain, lumps, masses, okay, like a mass that forms, microcalcifications, tissue asymmetry, and architectural distortion. Okay, so these are all the different outputs that are going to happen. Now, conditional probability tables. So, these are like, we are talking about a different example now. The conditional probability is alarm. Okay, so let's say you reached class on time or not on time. Okay, were you on time? Or what are the different things that can that can happen? Maybe the bus traffic, right? Bus was late, got caught in traffic, or maybe overslept. Why overslept? Alarm was on or off. So this is a directed acyclic or acyclic graph. Why? Because it's not one that goes one affecting the other. It could be this or that, and then the conditional probability tables, if one condition is true, then the other condition is obviously not met. Is this all making sense to you? Any questions on anything thus far?
Functional approximation as well as a probabilistic design are used to infer the knowledge. Okay. So should I repeat it? Okay. So there are two approaches to infer the knowledge from the data, right? First one is the function approximation and second one is the probabilistic reasoning. Now my question is to you, right? When should we use functional approximation and when should we go with the probabilistic reasoning? Because both have different algorithms. Would you please give me one example wherein the functional approximations would give you the better result compared to the probabilistic reasoning?
You should go with both.
Okay, so
because in function approximation, if you cannot integrate probabilistic reasoning, then you are missing the whole point of designing the algorithm. Is
Okay.
that making sense?
So ultimately, both are the different fields,
Yeah.
right? And there is no any disadvantage which can be overcome by the other one. Is it like that?
No, what? I'm sorry.
Madam, there are two different approaches, right?
Right.
Okay.
Then they are not real. They are two distinct concepts, but they have to come together when we actually design algorithms. Is what I'm trying to say.
Okay. So for better accuracy, we should implement both the methods, and we'll find it out which one gives you the better accuracy for the given problem.
Right. Correct.
Okay. Now, madam, it will be really hard to implement both the approach. It's really very tough to go with both the approaches because both have a vast number of the algorithms, and we cannot implement all the algorithms from both the approaches for the given application and find it out which one give you the best. So the basic questions to you is like, when the data set is linear, should we go with the functional approximations? When the data set contains polynomial approaches, wherein we should go with the probabilistic reasoning.
I'm talking about an unknown data set. So when
Yes.
you say if the data is this, which means you already know what the data and function is going to look like, then all the discussion that I'm doing is not going to apply because I'm talking about a data set which is unknown to you, where you are designing an algorithm, which is a completely different. If you say, if the data set is this, which means you already know the data set. So then there is no discussion of, then you can just go with whatever was done and then develop further and further to make it more a close fit as possible without overfitting.
True, madam, but in a given data set, we'll have a few independent variables, dependent variables, and there is some correlations among the features for the predicting the values or for the classifying the values. So even for the unknown data set, the features has some kind of the relationships based on which we can design the mathematical formula for it, right? So that is why the question comes to mind that when should we go with the probabilistic reasoning approach and when should we go with the first one,
The function approach.
yes, functional approximation.
If I were designing that's why I mentioned function approximation first, because that should be where it begins. And then when we actually have a function that matches, Then we can go with the probabilistic reasoning, saying, is this probable? Is this making sense? We might find features like, somebody has ankle injury. Okay, in that data set, maybe somebody had that, and that matches closely with breast cancer. Oh my God, there is a relationship, but that's illogical. You understand what I'm trying to say? So we have to. That's where our logic comes into play of the probability and logic, where we have to make sure. No, no, no. This is just spurious data that just the limited people had that issue, and that's why it happened. Okay, or only in Ahmedabad this happens. It's not like that. It happens all right. Okay, so did I help answer? Because first comes function approximation, then comes probabilistic reasoning. That's why I mentioned it in that order. Formula for conditional probability: A given B. We already know that. Intersection of A and B and then B. Naive Bayes used in AI, each event is independent of, that's why it's called naive. Naive is, naive, very innocent, right? Okay. Naive Bayes is because we assume every event is independent, like a flip of a coin. Okay. Now let's look at the Markov models. The Markov property, probability of transitioning to the next state, depends only on the current state and is independent of any preceding or past states. So Markov model is all about current state and future state, period. Okay? No past states. That's the whole idea. In short, current state determines future state. This is a stochastic model, refers to a random and unpredictable process. The memorylessness. Why memorylessness? Because no memory of past events. Okay, no past events memory. That's why memorylessness simplifies the model of sequential data. So current state, future state. Hidden Markov model is a variation, includes invisible states in addition to the current state. Okay, these are all something that we have to actually. I cannot teach you the Markov model in like 1 hour. Okay, so that is not possible. My job is to actually tell you what it is that you might need to learn more on your own outside this session to actually be able to design an algorithm. I'm not saying applying an algorithm. Application of algorithm is quite a different thing, okay? Because you are already taking the algorithms that already other people have designed, maybe make some minor variations. That's what happens in a lot of research. You take the algorithm, somebody, that is already available, that was done on data set, use that same data set, make minor changes, and, run the simulation and say, hey, look what my algorithm found. How many of you would agree with that kind of? Yeah, quite a few, right? Okay. So that is one way. I'm not saying that is a bad way or anything like that. That is accepted research. Okay, that is one way of doing research. The other way of doing research, no, I want to do something innovative. I want to do something different. What is it that you can come up with for a different type of how something works? It could be, particle swarm optimization. What are the different PSOs that you can develop? Anything like that. Then what do you need to know? Applications of Markov models are in finance, weather forecast, natural language processing. We used a lot of that, right? Large language models, so on and so forth. For example, the price of the stock depends upon several factors which actually are hidden, which remain invisible to the investor. Those are the hidden variables, okay? So they use Markov models, except that a lot of, even the algorithm like Google search, the algorithm that Google search uses, it is its IP, correct? It's not going to disclose the algorithm itself that is used, okay? So it is our job to develop an algorithm, and that would be our IP. One of you, like you can be an entrepreneur yourself. So we talked about the science of machine learning. Does anyone want to, have any comments on that or anything like that? Okay. So this is something we did in our lecture one. So I'm just going to go quickly through this slide rather than delve deeply on it. Just a overview. We talked about the science of algorithms. Now we are just talking about the different types, which is the reinforcement again, which would be robotic, the supervised learning, which would be the training data and test data, different applications for it, unsupervised learning, which is like clustering and so on and so forth. Okay, so what is a supervised learning algorithm? Analyzes the training data and produces an inferred function, which is then used to map new examples. Training data consists of a set of examples, pair input output. Why do I talk about it again? Because in function approximation, that is something we assume, right? That we will have an input and we will have an output and they will be related. Okay, so that's what that supervised learning is talking about, that algorithm that we are trying to design for it, that there is a pair of input and output. Okay? And I'm just showing how the raw data looks like in this picture, and the algorithm and the processing. Analyzes the training data set and then generalizes to unseen situations. That's the whole idea. So we know that, it learns all this that you see in the top slide, then it says, this is a circle, this is an ellipse, oval, whatever. Okay. Um, and then supervised learning algorithm examples, all classification and regression. Remember, we talked about regression as the best fit in stats. That same algorithms are supervised learning. And these are all many of you may, if you are doing research, if you are new to this field, you may not have actually used them, but otherwise, you may have actually used them in your own research. All these different, support vector machine SVM is a common one, same as random forest and so on and so forth, right? A lot of research happens with these. Okay, decision trees, of course, these are all supervised learning algorithm examples. The unsupervised learning task is to find the hidden structure in unlabeled data. Examples given to the learner are unlabeled, right? That's what the whole idea is to find out what is happening. And there is no error or reward signal to evaluate a potential solution. That is the biggest difference between reinforcement and supervised versus unsupervised. There is no reward, there is no way to know, am I doing it right for that algorithm? Okay, the algorithm doesn't know itself. All clustering algorithms, okay, hierarchical, hidden, Markov, k-means, of course. And so we have the algorithm, interpretation, processing, output. What is the difference between these two figures? Just a quick overview of what are they representing, each one? What is perfect. Okay, so just kind of remember the difference between the two. Supervised, as you can see, with books, learning with a lot of books, where you are just like, just out there. So let's begin with now. Let's link AI to it. Okay. So a lot of, like we talked about, AI is the buzzword, today. So AI awakens a range of questions on emotions in all of us. Anytime we talk about AI, it's like, what exactly is AI and how will it impact my quality of life? What is it? Goes from somebody who is 80 years old to all the way who is 8 years old, right? Okay, how is AI going to impact my quality of life? Physical, health, social, family and friends, economic, work, everything. So how will AI impact? Okay, we are all thinking AI is a boon because it is a perfect assistant. Frees up my time by handling routine tasks, answering queries supposedly intelligently, right? Okay, and taking meeting notes, hopefully meaningful, right? A lot of us, have you turned Otter AI on in lecture? Some of, yeah, yes. Okay, some allow, some don't allow. How many of you allow, have done that? Turned author AI meaning, note taking AI. Yes? How many of you actually use it? Can I see a show of hands? Oh, not that many. Okay. Okay. It is very common in the US to have, your AI tool take notes for you. So that's why I asked. Okay. So that's why I call it supposedly intelligently and hopefully meaningful, because many times the AI is going to mess things up. That is generative AI, correct? Anytime it is creating knowledge, basically. And here's some humor about generative AI. AI turns this single bullet point into a long email I can pretend I wrote, right? You give a query to ChatGPT, is going to come up with what? 100 sentences on one thing, one item. Or AI makes a single bullet point out of this long email I can pretend I read. So you feed something to an AI, like and you get Claude AI, whatever AI portal you may be using or you have an account, it's going to, can you summarize this in one sentence? It's going to give you, right? So that's generative AI. So, like we talked about, AI awakens a range of questions and emotions. But wait, we are thinking of, AI is it's just going to give us what it can summarize or something. It can be creative as well. Okay, that's why we had when she was talking, the vice chancellor was talking about the strike in the US. It was about the writers, right? It was the writers that were saying, hey, you can't use AI because we are generating the stories. We have already generated the stories. Now AI is already going to take those stories and kind of spin them around and create a new story for you. That's just like, that's not, we actually work. That is our IP, right? The stories that have been created by these writers, that is their intellectual property. Now AI is simply going to use the data set because it already has all these stories and going to spin a new story for you. So, so AI can be creative as well. AI is a threat because it can replace me at work. And that is true. Do you know what percentage of coding is done by AI today for major companies like Microsoft, Google, Facebook, whatever? The normal, like routine coders, 30%. 30% of the coding, routine coding, done by AI. So we talk about computer science, unless we talk about something, something that is high end or truly creative, then yes. But if it is something routine task, likely to be taken over by AI. Okay, so let's remember that, because we are still at the cusp of AI entering the work field. Is AI a threat to software jobs? Although AI is still largely immature, there are current and imminent uses of AI in application development, and the field is developing rapidly. I mean, what company is not going to use AI compared to actually human worker, correct? Okay, you call AI is here to stay and grow. We cannot fight AI. Who need not be threatened by AI? Everybody who is here. I'm honest, okay? Why are you here? Because you want to learn about AI. And everybody who is not threatened, those who understand what is AI and how to use AI. Where are the jobs that are going to come for future? How to use AI. Okay? What is this AI doing and how can I use it? How can I modify things? How can I use AI to achieve something? That's where the jobs are coming. So remember that. Everyone who is here, no threat, no job threat for you. But everybody who doesn't understand AI, then who says, that's it's not for me. No, we'll keep it away. Then that is a problem. So don't shun away from new technology that comes in. Embrace it, is my message. Today is AI, tomorrow is going to be something else. There was no AI as a buzzword or, just the technology being used 10 years before. It was used by defense. Always the technology trickles down from defense, even in US, okay? The internet, right? started, right, it was the Defense Research Agency that actually developed the internet all the way back in the 50s, 1950s. Slowly then it trickled into the everyday life. Okay, so remember that defense is way ahead. Okay, at least a decade ahead in technology. So who should not be threatened? Everybody who understands new technology and is willing to embrace the new technology. Okay, be willing to embrace it. Basics of AI: the search for anomalies, relationships, and global patterns that exist in large data sets but are hidden among the vast amounts of data, and using the findings to predict outcomes. Okay, that's what all AI is. The AI came because, hey, that data cannot be handled by human brain, correct? And therefore, because it's so big, technically our human brain is much, much bigger than what AI can do. But we are using only probably 1% of our human brain capacity, all of us. Okay, so we have to realize that. Executives seek to leverage AI for decision making. Okay, oh, data driven model. So give me the data. Tell me what is the data saying, right? What is the data saying? Innovative techniques to extract and use knowledge for strategic advantage. That's what the knowledge is. Knowledge is nothing but what are those insights that I can get from the data. Hourly temperature, humidity, precipitation readings for a rainy day, that's all data, right? We have all those readings, we have all that. Those readings organized in a continuum over the course of a day, that becomes information. Oh, we have all these graphs that we can see. That is information. Knowledge is taking those patterns and saying, hey, what can happen in these situations? What can happen in the future? That is where knowledge comes, identifying the pattern. As humidity rises and temperature drops, atmosphere can hold less moisture. So that insight is knowledge. And finally, applying that knowledge of that pattern, predicting the possibility of rain, is wisdom. So I'm just showing you like climate model, which is common for all of us, applies across the board for everybody. I'm just showing you what is data, what is information, what is knowledge, and finally, wisdom. So what is data mining, big data analytics, knowledge? KDD was a common word like maybe 2 decades ago. A new generation of computational theories and tools have been devised to extract knowledge from the volumes of digital data, resulting in AI algorithms. Remember, AI is a collaborative field, multidisciplinary effort, including computer science, math, stats, sociology, psychology. Don't underestimate the value of humanities, folks, right? Many of you are nodding and smiling. That is true, okay? I appreciate that you as technical folks appreciate the value of sociology, psychology, because without that we cannot really move forward in the whole AI field. Okay, so, and it is collaborative effort. You, the generation Y, millennials, and the generation Z, if you are born after 2000, you are the people that are blessed with collaboration. That is in your blood. Okay, so I truly appreciate that you have that already, that mindset of collaborating across disciplines. Make use of it. AI is enabled by machine learning algorithms. We already talked about that. Different ways to categorize AI. You might have learned weak AI and strong AI, right? Some of the things I'm just looking at, just giving you terminology, just so you become aware of, oh, this is how AI terms are used. Weak AI is nothing but simulated thinking. You just follow, you know how you write computer simulation program, if this then that, if this then that. That is exactly what simulated thing. If they ask for this query, then oh, bank balance. So you know how when we call nowadays, we just get the robot. What do you want? Bank balance, or do you want this, or do you want that? Same thing. No sense of whom it's talking to. It's the same general script for everybody. Strong AI, actual thinking like a human being. Not here yet. Okay, let's understand that. Strong AI, not here yet. How many of us self-driving cars are coming? They aren't really ready for the road. Okay, not ready for the road. Narrow AI versus general AI. Narrow AI limited to a specific set of tasks, right? Remember how the data set is available data set. It's only, so whatever is available, you design for that algorithm, cannot go beyond that. Okay. So IBM's Deep Blue, for example, Gary Kasparov. So just very narrow blinders. Okay. General AI used to complete a wide range of tasks, broad range of environment, closer to human. We can do multiple things. AI cannot be. AI is only very specific. Example? None, because it's not here yet. General AI is not here. Strong AI is not here. Super intelligence, we talk about it, not here yet, obviously, which is a combination really of general AI and strong AI coming together. That is human intelligence, correct? All of you. Systems that can generate creative content, theoretical concept not yet achieved. So we will talk about combining the two. You may have heard this term. Again, it is terminology that I'm just talking. Deep learning, machine learning, AI. Okay, so that's how it goes. What are ML algorithms? Enabled to learn, reason, and make decisions like humans rather than follow pre-programmed rules. Okay, AI and ML enablers. One biggest enabler, anybody who is in hardware. Everybody who is in hardware. And now India is manufacturing chips, right? Has this whole initiative about, hey, chip manufacturing. Great. Growing computer processing power and storage. Okay. Biggest driver of AI is the hardware, the capacity. How fast and how much can it store? Okay. And second, increasing data availability and accessibility. Now, availability and accessibility are two different things. Data is available. If you cannot use it, it's not accessible. You get the difference? Availability and accessibility. Accessibility is, can I use that data? That is accessibility. Okay? So, increasing data availability and accessibility, that's big data. I'm not talking about small projects that we do in our classrooms or one hospital data. No, one hospital data is small data. Multiple hospital data all over India, that would make large data, big data. Okay? What do we mean by big data? It's defined by 3 V's. You may have heard of the 3 V's and then the 5 V's, right? 3 V's, volume, velocity, variety. Okay? Volume, velocity, how quickly the data is created. So many people posting all the time on whatever social platforms. That creates huge data, the velocity. And then the variety. Some post text, some post pictures, some post whatever else, movies, videos, anything. The second one, very, very important now, especially with chatbots creating data. Have you heard of bots creating data? Right? Robots are creating data. With robots creating data, totally unreliable. They are just, veracity is zero. Veracity is truth. Truth to that data. Okay? The reliability of that data practically zero. So veracity is very important of the data set. Is this data created by a bot or is this actual data? There is a big difference between that. Okay? So be aware that beware. That's why be aware is beware. Okay? Of the veracity of a data set. You might get a data set. What is the veracity of the data set? You have to question it. And then finally value. Okay? What is the value? So big data just, just something that is totally mind-boggling. How much data is created in one day? 2.5 quintillion bytes of data created daily. How much is that? It's 250,000 US Libraries of Congress. And US Library of Congress is considered one of the largest actually libraries in the world. And 250,000 of those libraries, whatever the content is created in one. So it's just, that's big data. Why I'm giving you this example? Many times we say, oh, I'm working with big data. Okay, is it really big data or is it just data? Okay, is the question you have to ask yourself. So AI applications in everyday life, just simple, right? Education. Algorithms are used in for range of applications, including college admissions, dropout prediction, automated essay scoring. If you have taken all these entrance exams and somewhere, nobody, no human is scoring anything, correct? Even not even your essays, actually, to be honest. Okay. Criminal justice. A lot of, do you know that all the criminal courts in the US, many of the judges actually use whatever algorithms they are using. There is a big compass is the name of that algorithm, COMPAS, okay, not a double S. But that is a proprietary algorithm that is used in the criminal justice system to predict whether the recidivism is how likely is it that this criminal will repeat their criminal action. That is recidivism. And that actually determines what punishment to give, how much, and stuff like that. So that algorithm predicts it. There's a lot of issues with that problem, or with that algorithm. Okay, but they still, it's being used, and therefore they are applied to achieve fair, objective, and unbiased outcomes, because the judge can be biased, but hey, I'm using this algorithm. Remember, we try to say, hey, don't ask me, look at that, right? Healthcare algorithms deployed on clinical data sets for diagnostics. Many of these, like, great application for rural areas. So if any of you wants to develop a good algorithm for rural areas, this would be, and the diagnostics in India would be different from diagnostics in US, because obviously the social structure is different. What we eat is different. The patterns are life pattern is different. How much you walk, and there's hardly any walking in the US, for example. Everybody travels just by car. Here, every day you're walking either to the train station, bus stop, whatever. Okay. Human resource management. 55% of human resource leaders in the US use predictive algorithms in hiring. And this is all data, okay, that I got from, published articles. Financial services, banks use AI for credit worthiness assessment and loan approval. Remember, I already talked with you about that, about AI algorithms are replacing human decision making because they are perceived to be data driven while saving money and time. But data driven implies they are objective or unbiased, right? No human biases. How true is that? We already found that in the last example we did in the previous lecture, right? So humans are fallible while computers are logical and impartial and therefore infallible. How true or false is that? Right? I'm asking you. True or false? Like or yeah.
Somewhat work because multiplication algorithm is preferred by the human. If humans are fallible, then obviously the machines will be fallible.
Yes and no, because yes, we created, but we always say it is data driven. Because if we were to make a decision, we would make a decision based on our gut feeling, right? Many of us say, I have a gut feeling that, that this, I should do this. But if it is data driven, then it is different. So the algorithm is more data driven. When we make decisions, we are usually making them based on how we feel,
False positive could be there, madam.
Huh?
False positive could be there.
Yeah, correct. Yeah.
In that case, machine could be say the fallible.
Okay. That's true. An AI powered system is only as valid and reliable as the data that is fed to the ML algorithms. So, inadequacy of AI models are making decisions, and those decisions become data for future. We talked about flawed data, flawed decisions becoming flawed data, training data for tomorrow. AI models based on ML algorithms are a black box. The system uses big data and stated goals are assumptions to create outputs, while humans have minimal knowledge of its internal workings. Okay, fixing AI. One solution is human intervention to tweak the data set or algorithm. This is happening. Okay, tweaking the data set is not something new. It is actually happening, or algorithm design. Here are a couple of pictures of a Pope generated by AI. Pope is the head of the Roman Catholic Church. Any comments? Anything? Anyone wants to say? Look good? Look good? No comments? No comments? Based on this, what it generated, Google had to pause its AI tool, Gemini. Have you ever seen a pope who is a female? Have you ever seen a black pope? You understand? You know what is where this came from? Tweaking the data set. Remember I talked about here that first bullet point? That first bullet point talks about human intervention to tweak the data set for algorithm design. When you tweak the data set and you are not realistic, there is no reality in this picture that was generated. Oh, generated of the Pope. Black Pope, black female, black man. No, never has been a Pope. You see what happened? And then they had to stop because what? What kind of crazy thing is that? Because you ask something and it has to give you realistic answers, veracity. Remember we talked about that for big data. What is the veracity? What is the truth? Where is that truth that is coming from? It's going to give you some junk information. That's junk, right? This is anything that is not true and it tells you, oh, look, it's junk. It's not useful. So beware. Beware of, whenever you tweak a data set, don't tweak it just to put things in there that are not representative of what is happening in the real world. It is the message that this is trying to give you, that I'm trying to give you through this slide. Because Gemini produced historically inaccurate images that showed people of color or women in place of white men. That's why it had to pause the AI tool. And this is actual fact, okay? And such a recent fact. Such a recent fact. Why? So fixing AI with caution, okay? So that's be cautious when you try to fix something, fixing a data set, fixing with caution. So wrap up and takeaways and AI algorithm design and application summary. AI is here to stay. Organizations are not using AI, risk becoming obsolete. Same with people. Now, organizations, people, not different. If we have to learn how to use AI, perceived to be objective as data driven, save time and money, AI systems are not without flaws, right? My overreaching goal, influence the design, because I'm here to influence the design and deployment of AI, right? That's why you are here. I'm here to, actually educate you on this topic. Influence the design and deployment of socio-technical systems that broaden participation in the economy and lead to best outcomes for all subgroups of people, okay? As a consultant, I am a consultant in the US. Validate AI systems for predictions and automated decisions and ensure alignment with organization goals. So what are the organization goals? Are these predictions? Are they aligning? Alignment is very important. And create toolkits, scales, and assessment measures for the purpose of auditing AI applications. These are AI applications. Auditing them. Are they producing the results that we want them to produce? So quiz, okay? Ready? Last slide. What are the two enablers of ML algorithms from this group? Only one from this group, one from this group. What? Two enablers? Nobody remembers? Hardware. Now if I talk about the chip act, now chips, hardware. What was the second one? Perfect. Great. Both groups are excellent. growing computer processing power and storage, and increasing data availability and accessibility, big data. What are the scientific and underpinnings? One from here, one from here, or one from the back, one from the front. Last 4 rows, and then front 4 rows. Last 4 rows, one, anybody from the back. Loudly, I cannot hear you. Scientific or mathematical underpinnings, we discussed too. From the front row, you are from the front row. Go ahead. Excellent. Function approximation, that is taken. What is the second one? Somebody from the back. Yay! Good job. Excellent. Thank you. Thank you for making my day. Because that's important, that you are paying attention, that you are attentive. Why should we care about flaws in algorithm design? We want to make sure that we making AI fair and just. Okay, let's close with some humor about algorithms. I didn't do my math homework, but I've developed an algorithm that explains why. And remember, I said we will always close with a motivational quote. Who better than our own former president, right, of India? You have to dream before your dreams can come true. Okay? Whatever we dream, we can accomplish. Thank you.